Hello everyone, welcome to Chapter 14, Kinetics of a Particle, Work and Energy. The first lecture under this chapter is the work of a force. Before we go into work and energy, we are going to discuss the work done by a force. First of all, we go into the general definition of the work done by a force. A force does work on a particle when the particle undergoes a displacement in the direction of the force. Meaning, if you apply a force on your object and your object moves a certain distance, that distance, if it's in the same direction of the force or a component of the force, then you get a work by that force. If you apply a force on your object and it does not move in the direction of that force, then you get no work. So basically, work is defined as the product of force and displacement components acting in the same direction. So this is the mathematical definition. And if you have an angle between the force and displacement vector, that is theta, then increment of the work du that is done by the force is equal to f ds cosine theta, meaning you have your force F that, as you can see here, is acting upward. If you apply this force to this particle, okay, and as you can see, this particle has moved dr along this direction, and this force F has two components. One of them is cosine of the angle theta, that will give me this component. Then that component of the force will give me work. That's why we have du equals to F cosine theta multiplied by ds. Basically, ds is the scalar quantity of dr, as you can see in this figure. So, going a little bit into the mathematical definition to make it clear, mathematically, if you have two vectors, A and B, then the definition of the dot product is basically magnitude of A multiplied by magnitude of B multiplied by cosine the angle between them. Therefore, we can rewrite the work done by a force as du equals to F, the vector F, multiply dot product. This is a dot product. So F dot dr, which basically equals to F ds cosine theta, as we said in the previous slide. F ds cosine theta. So basically, if you want to integrate this from position, let's say 1 to position 2, where your ball has moved, then u from 1 to 2 will equal to integral from r1 to r2 f dot dr, which equals to the integral from s1 to s2 of f cosine theta ds. Now, regarding the force that is done by the force, whether if it's positive or negative, if you have the force in the same direction of the displacement, then you have a positive work. Even if you have a force that is not in the same direction but has a component, so if you look at this force, it has two components, one that is horizontal and one that is vertical. So the vertical one does not give me any work done because it's perpendicular to the displacement, and the horizontal component, which is this one, will give me positive work. So these are the first case. Second one, if you have a force similar to this one or similar to this one that is perpendicular, then work done is 0. So this F does not give me any work, whereas this F will give me two components. This one will give me work, whereas this one will not give me any work. And the work done is positive by these. Finally, if you have a force that is opposite to the displacement or has a component that is opposite to the displacement, then you get a negative work. Basically, you can rewrite these three as if theta is less than 90 degrees, then u is positive. If it's equal to 90, then you have no work done. If it's greater than 90, then the work is negative. Now, the unit of the work done by the force is joule. We use J for that one. And it is the amount of work done by 1 Newton force when it moves through a distance of 1 meter in the direction of the force. So you have F, which is the force times distance, which is basically Newton multiplied by meter. Or if you are using the British unit system, you have pound multiplied by feet. Now, let's go into our cases of different types of forces. The first thing, the most general case, is that you're going to have a variable force. When we say variable, meaning that the force will change in magnitude as it changes the location or as it moves forward. So in this example, we are going to move from S1 to S2, and they have a force F that is applied with an angle theta. Now, in this case, F and theta are functions of the position. So in this case, the work done u1 to 2 will equal to the integral from r1 to r2 f dot dr, as we know, which is basically the integral from s1 to s2, okay, which are the one that you can see on the figure to the right, f cosine theta ds. So this is the most general definition. Whenever you have a force that changes as you move from one position to another, you take the integral of that force multiplied by cosine theta between position 1 and position 2. And this is basically represented by the area under the curve. This is mathematically what's happening. If you have a curve, as you can see here, so basically you're crossing that curve to take the average in there. So you can see you have extra area on one side, less area on the other side. They balance each other to get the total area. Now, we go into more simpler cases. What if I have a constant force, which is most of the cases? So I have a force Fc that is constant. That means the magnitude of that force is constant as it moves from S1 to S2. Then, going to the integral that we talked about in the previous case, this F will be taken out of the integral, and this cosine theta will also be taken out of the integral. So I end up with F, so the work done between position 1 and position 2 will equal to F cosine theta integral from S1 to S2 of ds. Basically, this gives me F cosine theta S2 minus S1. So any constant force can be computed directly like this to give me the work done between the two locations. Now, we take more general cases. What if, more specific cases. What if I have the work of a weight? Weight is always a force that appears in dynamic problems. I'm always going to deal with force that is weight. So let's find a general expression for the weight. Now, considering the weight W of a particle, as you can see on the figure to the right, then the work can be rewritten as, first of all, we start with the general definition. The work done between 1 and 2 equals F dot dr, rewriting this as the integral from R1 to R2. Now, what is the work? It is W, and the magnitude is minus because it's minus J. I'm writing it as a vector, so it's minus Wj dot. Let's say I have a vector dr that goes from S1 to S2. So it's going to be some distance dx in I, some distance dy in j, and some distance dz in k. Now the dot product j dot I gives me nothing, gives me 0. J dot k also is 0. And then j dot j gives me 1. So I end up with w multiplied by dy. As you can see here, w multiplied by dy, and they have the minus from the minus w. So this ends up being minus w multiplied by y2 minus y1, which is the final elevation minus the initial elevation. So the general equation can be written as minus w plus or minus delta y. Now, a lot of students have some common mistakes when it comes to the work done by the weight, if it's positive or negative. You have two options to do this. The first one is mathematically as we have derived it. Always you're going to compute the work done by the force by saying minus W, and then, so I'm going to write it here, minus W, and then just open a bracket. Look at your problem. Identify the two positions, the first one where the problem started and the final one where the problem ends. Look at the final position and just write the magnitude of that y2 value. Just write it. Pick a reference point. No matter what reference point you are choosing, you can choose whatever you want. And you write y2 minus, from the same reference point, look at what is your y1. So in this case, this was my y2 and this was my y1. And write y1. This will correctly give you positive or negative. Now, another way of doing it, or let's say another way of checking whether your solution is right or wrong, we know that the work done by a force is positive if the force and the displacement are in the same direction, and the work done is negative if the force and displacement are opposite or are in the different directions. Now look at the weight. Weight is always acting downward. It's always acting downward. So if my object is moving downward, then I have a positive work. If my object is moving upward, then I have a negative work. Now, spring, the work done by the spring force. And this is also one of the forces that students sometimes have the same common mistake, and I'm going to discuss this in details. Now, the spring force always acts on the particle in the opposite direction to its displacement. And if you think of it, if you have a spring, as you can see in this part, and you are pulling it, okay, so the spring naturally would want to come back to its natural position. So it's going to push or pull backward. If you have a spring and you are pushing it with this force, so the spring will want to push you back to go back to its natural position. Therefore, the work done by the spring force is always negative, because the spring always gives you a force that is opposite to the displacement. So this is the first rule that we have to discuss. Now, let's derive the work done by the force, so by the force of the spring. So du equals to minus Fs ds. So I'm discussing how to write the work done by the spring force. And we know that the spring force is basically K times S. So I end up with having minus Ks ds. Now just integrate this between 1 and 2. I end up with integral from S1 to S2 minus Fs ds, which is basically, just compare these two with the integrals. So it's basically from S1 to S2 of minus Ks ds. Integrate this. K does not change with S, so it does not change with U. So the only thing you're going to integrate S ds. This gives you minus, and then you can see the minus is outside of the bracket, and then you have half Ks2 square minus half Ks1 square. Okay, so if the displacement of the particle and the force are in the same direction, then the work is positive and vice versa. This is what we said before. Now, where does the confusion come from? Confusion come from what is the definition of S1 and what is the definition of S2. Basically, S1 is, I'll go back to the previous slide just to show you that one. S1 or S2 is the amount of stretch or the amount of compression that you have in your spring. So this problem, let's say I moved from this point to this point. So this point is called S1, this point is called S2. When I go to S1, I will see, is this spring compressed or not? If it is compressed, I don't look at the length of that spring after it's being compressed. No, I look at the amount of compression. When I go to S2, I don't look at the final length of that one. I look at the amount of stretching that I have in that point. Okay, so basically I can write S1 or S2 if I want to write a general definition. Let's say any S1 will be, okay, current length, which is whatever you have at that location, current length, which is at location 1, minus unstretched length. Same thing with S2. It's the current length at position 2 minus unstretched length. Now, some problems will give you the unstretched length and length 1, length 2, so you have to do the subtraction. And some problems will give you directly the amount of stretching on, or the amount of stretching or compression. That is S1 and S2, and we're going to have some examples. The final force that we have is the work done by a friction. Now, friction always acts opposite to the force. If you look at this figure, you have an object that moves from this location to this location, so it is moving to the right. Therefore, I'm going to have friction to the left. As you can see here, this is the direction of the force, this is the direction of the friction, it's opposite. Therefore, the work done of the force would be P times S, P multiplied by the distance S that it moved, minus the friction force times S, which is mu K times N, this is my Fs, times the distance S. So we'll take a general example that will show me how to calculate the work done by all these forces, and we're going to calculate each one of these. So let's look at this problem. The 10 kilogram block shown in figure 16.4 on the right rests on the smooth incline, so there is no friction in this problem. If the spring is originally stretched 0.5, originally, so this was the original position, and this is my final position. So it rests on the smooth incline. If the spring is originally stretched 0.5 meters, determine the total work done by all the forces acting on the block when a horizontal force equals 400 Newton pushes the block up the plane by a distance S equals 2 meters. Keep in mind, this S equals 2 meters is not horizontal, this is inclined force. So let's look at the free body diagram that we have in here. So you're going to have the force, so this is your block, you have the force equals 400 Newton acting to the left, and it has an angle theta given to me in the problem. So this is your angle theta. You have, it's going to slide upward, so I'm going to have a friction force acting downward. I'm going to have the weight acting downward, and normal to the surface, I'm going to have a normal force. It's interesting to note that normal forces always gives you zero work, because it is always normal to the surface. And if you have something moving along a surface, then that normal force will be perpendicular to it, so it gives you zero. Now, let's start with the work done by the horizontal force P. So basically, I'm gonna write the work done. So UP will equal to, in this case, the force, which is 400 Newton, multiplied by the distance, which is 2 meters, multiplied by the angle between them. Remember that I need to take cosine the angle or the component. Now, if you are having always problem with finding which angle, do I take sine or cosine, look at your object. So this is my object, and this is my force that is applied. Now, always identify your coordinates in this problem. Coordinates are related to the movement. So I'm moving along the incline, so I can say that this is my x-axis, and perpendicular to it I'm going to have, sorry, so this is not clear. So this is my x-axis, and this is my y-axis. Okay, I'm going to extend these two. So always, when you have two coordinates, x and y, once you identify them, make the angle between them 90. So it's going to look something like this. So this is 90. Now I can write that this angle is 30 degrees. Now you know that you're going to take cosine the angle between the force and the displacement to give me the horizontal component of force P. So PH, horizontal component. So it's going to be 400 Newton times 2 meters multiplied by cosine 30 degrees. And this is going to give me, if you take the if you carry out the calculation, it's going to be 692.8 joules. So this is the work done by the horizontal force P. Now let's look at the work done by the spring force. Okay, so if you remember, we said that the work done by the spring will equal to minus, and then you open a bracket. We said we have half K S2 square minus half K S1 square. Now let's identify what is S1 and S2, and then I can take out the carry out the calculation. So S1, if you read the problem, it says that the spring is originally stretched 0.5. Remember, this is my position 1 and this is my position 2. So in position 1, I don't need to say current length minus unstretched length. I already have the amount, which is equal to 0.5. So it is 0.5 meters. And what about S2? Now, in position 2, I don't know the complete length of the spring because this part is unknown. So I don't know that, but I know the complete or the amount of stretching. Basically what I have is, originally it was stretched 0.5 and then it moved 2 meters. So it was a stretched 0.5 and then you stretch it an additional 2 meters. So it's going to be 0.5 plus 2. This equals to 2.5 meters. Now, if it was originally compressed 0.5 and you pulled it 2 meters, it's going to be 2 minus 0.5 in that case. So writing the work done by the spring now becomes straightforward. So it's equals to minus, open a bracket, 1/2. You have the spring constant, which is given in the problem, in the figure, which is 30 Newton per meter. So it's going to be half multiplied by 30 multiplied by 2.5 square minus half multiplied by 30 multiplied by 0.5 square. Close this one. If you carry out the calculations, you end up with minus 90 joules. And this is the work done by the spring force. Finally, we calculate the work done by the weight. So U done by the weight, it's going to be, remember, equals to minus W plus or minus delta Y. So it's going to be minus the weight is going to be M times G. So the mass is 10. So you have minus M, which is 10. Gravity is 9.81 multiplied by delta Y. What was the final position? Just pick any position that you want. If this was my reference, so I'm going to take the original location as my reference. Okay, so it moved from position 1 to position 2. So what is the elevation at position 2? Remember, this is 2 meters. This angle is 30 degrees. So the vertical component is 2 multiplied by sine 30. So it's going to be 2 sine 30 degrees minus, since I'm choosing position 1 to be my reference, it is 0. And this gives me, if you carry out the calculations, it's going to be minus 98.1 joules. Okay, And this covers all the forces that we have. Now finally, if you want to find the final value of the work done, basically you just add all of these. So the total work done will be the first value that we got for the force. It was 692.8, then minus 90 minus 98.1, and this gives me a total of around 505, something like this. Okay, and this basically covers all types of forces that we may face in dynamic problems. And with this, I'm going to thank you all for listening and conclude this lecture.